everyone, I'm Dr. Rizwana, working as Professor of Physics in Institute of Aeronautical Engineering. In my previous videos, we have discussed in detail about semiconductors, their properties, and then we have discussed different types of semiconductors. And then after that, we have discussed about intrinsic semiconductors. And then we have calculated intrinsic carrier concentration in terms of electron concentration and hole concentration. And also we have seen what is the location of Fermi level in intrinsic semiconductors. Then after that, we have discussed in detail about extrinsic semiconductors, which are impure semiconductors. And in that extrinsic semiconductors, we have discussed about N-type semiconductors. So in N-type semiconductors, we have seen carrier concentration in terms of donor concentration, and also we have located Fermi level. We got expression for Fermi level in N-type semiconductors, and there we have observed that at T is equal to 0 kelvins, Fermi level, it is exactly middle of donor energy level and conduction band. So now same way we are going to explain in detail about P-type semiconductors. Coming to P-type semiconductors, so today our topic of discussion is carrier concentration and Fermi conductors. Now what are P-type semiconductors? As we have already seen that extrinsic semiconductors are formed when we take intrinsic semiconductors and when we add impurities or dopants. So depending upon what type of impurity or dopant we are adding, we have two types of extrinsic semiconductors. One, N-type semiconductor, and second one is P-type semiconductor. And N-type semiconductor, it is formed by doping pentavalent impurity. And these pentavalent impurity, they have this tendency of donating their electrons to the conduction band of intrinsic semiconductor. Now coming to our P-type semiconductor, so here in this case what we'll do, we'll take intrinsic semiconductor and to that we'll add trivalent impurity. So in this case, what type of impurity we are choosing? We are choosing trivalent impurity, and these trivalent impurities, they belong to group 3. So these trivalent impurities, they belong to group 3, and group 3 means generally these impurities, they have 3 valence electrons. Okay, so what are the examples of these group 3 elements? As you can see, boron, aluminium or gallium. Now all these elements, they have 3 valence electrons and they are called as trivalent impurities. Now we'll see what happens when we add such trivalent impurities to intrinsic semiconductors. Now already we have discussed that what is our intention behind adding impurities or dopants to intrinsic semiconductors. See, in intrinsic semiconductors, we have seen that in order to make them conductors, we have to go to very high temperature. And we want to make these semiconductors conductors at normal temperature or moderately low temperature. So that's why what we have done, we have added dopants. And what is the role played by these dopants or impurities? What they'll do, they'll increase charge carriers at moderately low temperatures, and they'll also increase electrical conductivity of the semiconductor. So we are able to make them conductors even at moderately low temperatures. So we don't have to go to high temperatures. So now we'll see, as in N-type semiconductors, there we are able to get electrons as majority charge carriers. And here we'll try to see what type of charge carriers and how we are able to increase electrical conduction at moderately low temperatures by adding such trivalent impurities. And that we can better understand by taking this figure. So in this case, what we have done, so here, what type of trivalent impurity I have added? I have added boron. We have seen that examples are boron, gallium and indium. And here I have taken boron. And already we know that this boron, it has got 3 valence electrons. So here when I have added one boron impurity atom to intrinsic semiconductor, then what this boron is going to do, it is going to form 3 covalent bonds with adjacent silicon atom. This is first covalent bond, second covalent bond, and then third covalent bond. Okay, then what about the fourth bond? So what you will observe here is, in this case, as you can see, this intrinsic atom, it needs one electron in order to form bond with boron. So what this silicon will do, it will give its electron to boron, or boron, it will accept electron from intrinsic atom. See, generally group 3 elements, they have this tendency of accepting electrons. So they have this tendency of becoming negatively charged. So what they'll do, they'll try to take that electron in the 4th bond and they'll contribute hole to the silicon atoms. So that we can understand. So here what is happening in the 4th bond position, here we are getting one hole. Okay, so that we can understand by using this energy band diagram. Now this is our valence band and this is our conduction band. Now what you will observe here is EA. Now we are coming across one more energy level, EA, that is called as acceptor energy level. And as you can see, what is EV? EV, it is top of valence band, and we know that EC is bottom of conduction band, and at normal condition we know that valence band is filled with electrons. Now what you will observe here is, coming to this EA, what is EA? It is called as acceptor energy level. Actually, it's the energy level of travelent impurity. So if you take this EA, which is acceptor energy level, and this acceptor energy level, this is nothing but energy level of the travelent impurity. So this energy level of travelent impurity is nothing but acceptor energy level. Now if you see this acceptor energy level, we have kept it close to valence band. Whereas in case of N-type semiconductors, we have taken donor energy level, and the donor energy level, it is close to conduction band. Why we have taken close to conduction band? Because donor energy level, it will be occupied by 5th free electrons of donor impurities or pentavalent impurities. But in our case, what is the tendency of travelent impurity? It will try to take electrons from intrinsic atoms. It means that this atoms, so they have this tendency of contributing holes, and we know that for holes energy level, it is close to valence band. So that's why we have taken this acceptor energy level close to valence band. And if you take room temperature, at room temperature you will observe that our acceptor energy level is empty. So this travelent impurity, it has not taken electron from the intrinsic atom. Now if we slightly increase our temperature at moderately low temperature, now electron transition takes place. And from where to where electron is going to move, you will observe that there will be transition of electron from valence band of intrinsic atom to acceptor energy level. Okay, so now we have our electrons going from valence band to acceptor energy level. Then what happens to our this particular travelent impurities? Because they are taking electrons from valence band of intrinsic semiconductor, they will become negatively ionized. So they will become negatively ionized, and once electrons goes to acceptor energy level, what is left in the valence band? You will be left with holes. So you'll be left with holes. Okay, and so here now we are able to get holes in the valence band without any involvement of conduction band. But in intrinsic semiconductors, we have seen that we will get holes in the valence band only if electrons jump from valence band to conduction band, and that happens only if you go to higher temperatures. But here we didn't go to higher temperatures, we are at moderately low temperatures. Still we are able to get holes in valence band without any involvement of conduction band. So here we'll get majority charge carriers as holes and minority charge carriers are electrons. And this particular travelent impurity, because it is accepting electron from valence band of intrinsic semiconductor, it is called as acceptor impurity, and they have this tendency of becoming negatively ionized. So I hope you are able to understand why here holes are majority charge carriers. So even at low temperature, we are able to get charge carriers, and these charge carriers increase electrical conductivity property of these p-type semiconductors. Now next, what we'll try to do, we'll try to get expression for carrier concentration in p-type semiconductors. Now what we have done in case of intrinsic semiconductors, because in intrinsic semiconductors we have equal number of holes and equal number of electrons in both valence band and conduction band, we derived expression for both electrons and holes. But in n-type semiconductors, majority charge carriers are electrons. So there we have derived expression only for electrons. Now here majority charge carriers are holes in p-type semiconductors. So we'll try to get expression for density of holes, and where these holes are present, they are present in the valence band, and that density of holes we have to derive in terms of this acceptor energy level as well as acceptor concentration. How many number of acceptor impurities we are adding per unit volume of intrinsic semiconductor. So that we are going to proceed further now. So we are trying to derive expression for carrier concentration in p-type semiconductors. Now what I have done here, let Na be the acceptor concentration. So what do you mean by acceptor concentration? How many number of acceptor atoms are being added per unit volume of intrinsic semiconductor? It is called as acceptor concentration. And of course, EA is our acceptor energy level. We have seen in the previous energy band diagram, acceptor energy level, and we know that acceptor energy level, it is close to valence band. Now we are saying that at room temperature, acceptor energy level is empty. So if you see this figure, suppose I am drawing this figure again. This is our conduction band. This is I think bottom of conduction band, and then we have EV, which is top of valence band, and then we have EA, which is acceptor energy level, which is kept close to valence band. And first when we are adding, what you will observe here is these travelent impurities, they have not taken electrons from intrinsic atoms. So that's why we'll say that acceptor energy level is empty. Now when we go to low temperatures, when we increase our temperature, then what you will observe here is there will be transition of electron from valence band to acceptor energy level. It means that our acceptor atoms are getting ionized. Then what will happen in valence band? We are left with holes. And what happens in acceptor energy level? You will be left with negatively ionized acceptor impurities. So that is what we are going to see here. So as temperature increases, what is happening? More acceptor atoms, they'll get ionized, and electrons, they are going to take transition from valence band to acceptor energy level, leaving holes in the valence band. Now we'll try to get expression for concentration of holes in valence band per unit volume in terms of this acceptor energy level as well as acceptor concentration. So for that, we are making use of density of holes in the valence band that we have derived in case of intrinsic semiconductor. So density of holes in valence band, of course, it is given by notation P. Why P? Because these holes, they are assumed to be positively charged, and whereas in case of density of electrons, we have used notation N, and N represents density of electrons in the conduction band. Why? Because the electrons are negatively charged. So here, density of holes, it is given by P. And what is the formula we got in case of intrinsic semiconductors? It is given by 2 into 2 pi MP star. What is MP star? Effective mass of hole. I think already we have discussed about effective mass of hole. Effective mass of hole is nothing but where mass of hole is going to vary with velocity when your electron is accelerated by electric or magnetic field, and that electron, it is moving in a periodic potential. And of course, KB is our Boltzmann constant and H is our Planck's constant. Now as you can see, exponential of, so what is present here? Minus of EF minus EV, or this can also be written as EV minus EF by KBT. And what is our EV? EV is topmost of valence band, and EF is our Fermi energy level. Already we have defined about Fermi energy level, whose location and whose definition, it is going to vary with temperature and also with the material. Now next, how to know how many number of acceptors are taking electrons from valence band of intrinsic semiconductor. So that is nothing but we have to know what is the density of ionized acceptors, how many number of acceptor atoms are present per unit volume. So for that, what I have done, how many number of acceptor impurities I have added? Na number of acceptor impurities into F of Ea. What is F of Ea? We know that F of E is Fermi-Dirac distribution function. And what is Fermi-Dirac distribution function? Probability of an electron occupying, if we take suppose F of E. What is F of E? Probability of an electron occupying an energy level E. And here we are talking about F of Ea. It means that what are the chances of an electron occupying acceptor energy level. I think this is what happening in our p-type semiconductors. As you can see, electron, it is taking transition from valence band to acceptor energy level. So that's why we'll take F of Ea. So out of total number, Na number of acceptor impurities added, how many have taken electrons from valence band of intrinsic semiconductor? That is nothing but how many acceptor atoms have they have become negatively ionized. So that is given by this expression, and already we know what is the expression for F of Ea. We have seen that F of E. So when we are deriving the expression for intrinsic semiconductors, there we have seen that F of E is exponential EF minus E by kBT. Of course, where EF is our Fermi energy level. Now in place of E, here we have acceptor energy level. So it will become EF minus. So this I can also write as EF minus EA by kBT, where kB is Boltzmann constant. So this is the expression for ionized acceptors. So we got expression for density of holes in valence band, and we got expression for density of ionized acceptors. Now what you will observe here is, in this case we have not gone to high temperature. What happens if we go to high temperature? When we go to high temperature now, transition of electron takes place between valence band to conduction band. It means that electron hole pairs are generated, and how they are generated? Because of breaking of covalent bonds. But because we are not going to high temperatures, we are at low temperatures, and there is no involvement of transition of electron from valence band to conduction band. So I can simply say that density of holes in valence band, it is nothing but density of ionized acceptors. So number of holes formed in valence band of intrinsic semiconductor, it will be equal to how many number of acceptor atoms have become negatively ionized, and it is so only at low temperatures. Why? Because if we go to high temperatures, then we cannot say that holes will be equal to what? Why? Because now these holes, some more holes may be generated at high temperature because of electron taking transition from valence band to conduction band. So what we are saying here is, at very low temperature, when electron hole pairs are generated due to breaking of covalent bonds, actually they are not generated at low temperatures. So density of holes in the valence band, it will be equal to density of ionized acceptors. So now carrier concentration in p-type semiconductors, how it is given? What is the notation for carrier concentration in p-type semiconductor? It is given as P extrinsic p-type, and this P for density of holes, and density of holes where? In extrinsic semiconductor. And what type of extrinsic semiconductor we have taken? P-type. Okay, so P stands for density of holes, or because majority charge carriers are holes, and it is nothing but density of holes in the valence band, which is equal to density of ionized acceptors. Now if I try to multiply expression for density of holes in valence band and density of ionized acceptors, then I'll end up having square of carrier concentration in p-type semiconductors. Now we are going to multiply expressions for both density of holes and density of ionized acceptors. When we do it, we end up having this as 2 into Na. What is Na? Na is acceptor concentration into 2 pi mh star kt by h square whole to the power of 3 by 2. And then if we simplify these two exponential terms, we end up having exponential EV minus EA by kBT. This is what we'll get. Okay, so when we multiply both these expression for density of electrons as well as density of ionized acceptors, we'll end up having this expression. But here we have taken square. So in order to get a carrier concentration in p-type, then whatever expression we got for this, we have to take square root. And when we take square root, here we'll have 2Na whole to the power of half. And this 3 by 2 into half, it will become 3 by 4. And here it will be exponential EV minus EA by 2 kBt. So it will become 2 kBt. So that is what we have written in this case. So what is the concentration here? 2Na whole to the power of half. 2 pi mh star kBt by h square whole to the power of 3 by 4 exponential EV minus EA by 2 kBt. So this is the expression for carrier concentration in p-type semiconductors. And when we say carrier concentration in p-type semiconductors, we are talking about where we are talking about only density of holes. And if you see here, this carrier concentration in p-type semiconductors, it is proportional to square root of acceptor concentration. This we have to remember. So number of holes that are formed in the valence band, they will be proportional to square root of acceptor concentration in case of p-type semiconductors. Whereas we have seen that in n-type semiconductors, density of electrons in the conduction band, it is proportional to square root of donor concentration. So here in this case, it is acceptor concentration. So we got expression for carrier concentration in p-type semiconductors. Now next we'll see what is the location of Fermi level in p-type semiconductors. So now again we are going to use same logic as we have used in order to derive expression for carrier concentration in p-type semiconductors. So in this case, again same thing. What we are doing, we are not going to high temperatures. What happens when we go to high temperatures? Then now transition of electron takes place from valence band to conduction band. Then some more holes are being generated. So we are avoiding such formation of hole in valence band. We are at very low temperatures. Now transition, it is taking place only between acceptor energy level and valence band. So that's why number of holes that are formed in valence band, they'll be equal to number of acceptor impurities becoming negatively ionized. So same concept again we are using in order to find Fermi level in p-type semiconductors. Now what I am going to do, I am going to equate expression for density of holes in valence band as well as density of ionized acceptors. Now I'll take all exponential terms to left hand side and then all other constant terms I'll take to right hand side. Now I'm trying to simplify all exponential terms. So if I simplify, I end up having minus 2EF. So this is e to the power of a by e to the power of b, and we know that e to the power of a by e to the power of b will be e to the power of a minus b. Same thing we are going to use here. And when we do it, I end up having it as minus 2EF plus EV plus EA by kBt. And what we have on the right hand side, we have one ratio which is Na by 2 into 2 pi mp star kBt by h square whole to the power of 3 by 2. Now what I'll do, I'll try to remove this exponential term. So if I want to remove this exponential, I have to take logarithms on both sides. So I'll take logarithm, then I end up having minus 2EF plus EV plus EA by kBt. It is equal to log of this particular constant term. Okay. Now I'm taking this kBt onto the other side. After that, again I'll take this EV plus EA on the other side, and also what we are going to do, we are going to take this 2 to the other side, so that we should get expression for Fermi energy level. So when we rearrange the terms, when we simplify this equation, we end up having expression for Fermi energy level in p-type semiconductors as EV plus EA by 2 minus kBt by 2 log of this particular constant term. So this is the expression for Fermi level in p-type semiconductors. Now, what I am doing in this particular expression, I am assuming that let temperature is equal to 0 kelvins. Now, once I substitute temperature is equal to 0 kelvins, then I end up this second term becoming 0. So, when your second term becomes 0, when it becomes 0, then what is left are Fermi energy level. It is given by EV plus EA by 2. What does it mean? It means that at T is equal to 0 kelvins, our Fermi level, it is exactly middle between top of valence band and acceptor energy level. So if we try to represent it in terms of energy level diagram, so I have my conduction band and there is no involvement of conduction band in case of p-type semiconductors. Then I have my valence band and there is one more acceptor energy level which is taken close to valence band. So at T is equal to 0 kelvins, where is our Fermi level? Fermi level is exactly middle between valence band, that is the topmost energy level of valence band, and acceptor energy level. So what is our EF here? EF is EV plus EA by 2. Okay. So this is the location of Fermi level in p-type semiconductors at T is equal to 0 kelvins. And whereas in n-type semiconductors, what is the location of Fermi level? In that we have taken again conduction band and valence band, but there is no role played by valence band. We have donor energy level. What is donor energy level? Energy level of that fifth electron of donor impurity, and it is close to conduction band. And at T is equal to 0 kelvins, we have seen that its Fermi energy is exactly middle of conduction band, bottommost energy level of conduction band and donor energy level. So this is the case we have seen in case of n-type semiconductors. Now whereas in intrinsic semiconductors, where is our Fermi level? If we take EC to be the bottommost energy level of conduction band and EV to be topmost of valence band, then our Fermi energy level is exactly middle. Okay, or it is exactly middle of forbidden energy gap, and in that case EF, it is given as EC plus EV by 2, exactly middle of forbidden energy gap, or it is between the middle between the topmost energy level of valence band and bottommost energy level of the conduction band. So here we have seen that even though we have same temperature, location of Fermi level, it is going to change from one type of material to another type of material. So in our next video, we'll explain how this Fermi level is going to change with temperature, and also what will happen when your donor as well as acceptor concentration in n-type and p-type are changed. So now we are going to end our session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.